This is a joint presentation of myself and Greg from Undo about extreme stress testing and how we improve software quality of SAP HANA using Undo. To set the stage for what we do on the stress testing side for HANA, let me first introduce what the product itself is. So SAP HANA is an in-memory enterprise class database that is handling OLTP and OLAP workloads on a single copy of data. It's mainly relational, but it's not exclusive bound to that. So HANA also contains a bunch of engines and possibilities for NoSQL functionality, like graph engines, document stores, text processing, text analysis, and a bunch of different additional things, which also means it's a fairly complex code base to test. And what we are doing, because there is mission-critical systems running on it, is having a very strict quality process and governance process that is running fairly sophisticated continuous integration platforms that cover both things like functional testing, but as well as performance testing, right? And also how we can compare different versions of the system against each other, right? In terms of performance regression and things. And Kim Thomas shared things there in RDSS 2014. Now, the regular tests are complemented by parallel multi-user stress tests, what we call PMUD. This is actually arbitrary database operations, so DDL, DML statements, and everything else that put a high amount of stress on the system in a way that is kind of non-deterministic, right? So to figure out what are kind of random situations and things that you typically don't test in a static test. You can compare this to kind of a chaos monkey kind of a thing on the database workload side. Now, the good thing about this is these sort of tests on the parallel multi-user testing side are capturing a lot of sporadic issues that you usually don't find, right? And it's good that we find those things in-house instead of bumping into these situations on productive systems on our customer side. The bad thing about it is, due to the non-deterministic nature of the testing, it's fairly hard to reason about it and to find what the root cause is. So usually it takes developers hours and days and weeks to reason about the root cause and find the root cause and get to the point. While fixing the issue later on is usually a kind of trivial thing, right? Once you know what the root cause is. And the question is, how do we optimize the process on identifying the root cause in these non-deterministic things? And the solution for that is the LiveRecorder of Undo. And let me hand it over to Greg to explain how that thing looks.
Okay, so as Stefan was saying, you have an extreme stress testing setup that can trigger these edge cases. And when you get the failure, what do you do with that? How do you track that back to what you have? And actually, there's a nice metaphor for debugging from Brian Kernighan and Rob Pike, which is that it's like solving murder mysteries, right? And you have the impossible that has occurred, and all you know is that, well, actually it did occur, so somehow it must be possible, so how do we know? And debugging often then is like some kind of, Sherlock Holmes kind of brilliant deduction of like there's a dead body on the floor and a smashed vase, and you have to kind of figure out what happened. But these days, of course, we can just use CCTV, right? Get the video recording, see what happened, and that takes, maybe takes some of the fun and glamour out of it, but gets you to the answer much more quickly and much more certainly. We want to be able to do the same with software, right? So when we've got this, the equivalent of the dead body on the floor is perhaps a core dump, right? What happened leading up to that? And with LiveRecorder, that's what we've created, is a system to capture the execution of the software, It's kind of like a core file, but it has time in it as well. And then you can load that core file up and go back in time and see precisely what happened and wind that tape back and forward. And what the developer sees is just like a classic debugger view, right? So this is my kind of mocked up demo inside PowerPoint. So this is showing, this is the Sea Lion IDE. That's kind of unimportant, right? This plugs into whatever IDE you want. So people use it in GDB command line or whatever, but this is somewhat more visual. So here we are, a very simple program, and I can see it's at this assert 0, right? So clearly it's gone wrong. But in this debugger view, what we can do is select this button here, this reverse step over, right? So reverse step, just like traditional debugger lets you step forwards through code, this is going to step backwards. The other difference to bear in mind is this is something that happened some time ago, right? Maybe this failed yesterday or last week or whatever. But now we can step back. So if I click that, we go back one line, and I can see where we've come from. If I go back again, we can see that I have a pointer here, the data here changes, right? So it's not just a history of where my program counter has been. We can actually see the locals and the global state unwinding. And I can kind of see that, okay, so this test has failed, which has ended up calling assert 0, and this is essentially this function here, cache calculate, has returned the wrong thing. So if we go back once more, and now I'm going to instead click reverse step into, so we can go inside that function and see why it returned what it did. And so from here we can see that, okay, it's returning the wrong entry from a cache, and I can actually now select that data and apply a watch point, or a data breakpoint, and then hit this button over here, this reverse resume button, to go back in time until that data changed. Right? And so using that mechanism, you can sort of follow the thread through a program execution and get to the bottom of what happened. Now this is in order to implement this, we have to capture all of the non-deterministic stimuli to the program, right? And there's been a few talks that have mentioned determinism and the problems that brings in. Now, of course, the kind of most obvious or main source of non-determinism to a program is its inputs, right? So in the case of the database, it's the queries that are coming in and the data that's being read off the persistent store. But that's only one source of non-determinism. We also have things like concurrency, threads and thread switches. We have asynchronous signals, things like that. Accesses to shared memory, right? Most memory behaves that you read back from the memory what you most recently wrote, but if the memory is shared with another process or DMA from a device, maybe you read back something different next time, right? And actually there's some CPU instructions that are non-deterministic as well. Read the timestamp counter is one, there are several. So most kind of fuzz testing approaches are able to have a kind of pseudo-randomized input so that you can replay precisely those input, the I/O, the inputs to the program, but they don't deal with those other sorts of non-determinism. And that means for these really nasty bugs, the race conditions and the memory corruptions, they probably don't happen the same each time. Well, when you're recording with LiveRecorder, it's guaranteed 100% reproducible. And coming back to what Stefan was saying earlier about the time it takes to root cause that, right? I think if you think about what makes bugs hard to track down, there's kind of two axes. One is how long elapses between the problem itself and the manifestation, right? The core file being generated or the assertion failing or the wrong result being delivered. If it's very close, if you just read some pointer and dereference a null pointer when you should have just checked for null, you can look at the core file and it's pretty obvious what's happened. The longer has elapsed, the harder that is. Then the other axis is kind of how deterministic is it? Does it fail in the same way each time? And when you're kind of out on the top right on that chart of those two axes, that's when life gets really, really challenging. And you get these issues that are basically just not practical to debug, right? So that's kind of the high-level view of kind of what this does. Let's look at some real-world examples of how this has been used to capture those issues inside HANA before they get out into the wild, right? Before the customers encounter them. And some of these things are examples of things that are just really, really tough to capture and diagnose internally. So good examples of things up on that top right-hand corner of non-deterministic and long time between the problem and its manifestation is the sporadic memory leaks and memory corruption, right? Memory corruption is a classic. You scribble, so over some piece of data, and when do you notice? Who knows? Some arbitrary time later, billions of machine instructions later, usually. Memory leaks, again, sometimes the memory leak is obvious, like you just have you can track the memory allocation and deallocation, and you can use fairly standard existing tools to track those memory leaks, and sometimes you can see, oh yeah, there was a return here that just like forgot to call free. I've just got a malloc without the matching free, and they're easy. But often it's much more, it interacts with it. There's a reference counting bug, for example, and some reference count somewhere wasn't dropped some time ago, right? How do you track those down? Some of these other cases around the networking code, right? And networking is that's I guess, a specific case of interaction with DOS when things aren't always so simple. So I don't know, maybe a read returns short, that nearly every time it reads completely, but sometimes it returns short. Do you handle that every time, right? And those sporadic, again, those sporadic failures that just go differently each time. Race conditions, right, is a classic. So you can feed the same queries, the same set of data 1,000 times, and it works just fine, and then there's that one rare one that goes wrong, right? And of course, in this kind of world, in this database world, if it's 1 in a million, well, in production, that's going to happen all the time, right? But in test, it's really hard to do anything with those 1 in a million failures. Here's another nice one. I mean, the value of catching these kinds of problems in tests before they're released, so returning the wrong row of the database, that's the kind of thing when it happens in production, like, does anybody even notice, right? And then, but like maybe they do, and maybe something really bad, or clearly there are very serious implications if that happens in reality, but then, like, it's when you get those, was I dreaming that? Like I can't reproduce it, I've never seen it before or since. But the implications can be really bad. So being able to capture these inside PMUT and not only capture them, but diagnose them and fix them efficiently is really powerful. Another example of a race condition. It's kind of combines some of these other things as well, right, with the kind of the reference counting problems that I mentioned earlier. This is very common, and in fact, pretty much every large-scale software development organization I talk to seems to have this problem of ever-growing number of tests that fail, and nobody knows why, right? And I think as a software industry in general, we've got much better at testing much more exhaustively over the last 5, 10, 15 years. I think a typical software project is probably running orders of magnitude more tests every hour, every week than it would have done 10, 15 years ago. But this has implications. And then when we get these low failure rates, 0.5% of the tests are failing, or 0.05% of the tests are failing, that's a lot of failures. And being able to practically triage them and just be able to do something other than go, I don't know, it's one of those weird things. I can actually now get in and fix it and release higher quality code. So I gave my crummy demo on in PowerPoint. If you want to see a real demo of this working, then there's some Undo folk at the back who can show you that in the break if you haven't already seen this stuff. Otherwise, yeah, thank you for listening, and any questions.
I think yes, there is still cases where we can't explain, but they get much rare, right? Because a lot of things get easier or quicker understandable and reproducible.
Yeah. So actually, it's not implemented by tracking the register state as you might think. Partly because exactly the reason you mentioned, right? So what we wanted to do is we wanted to build a system where you could go back to any instruction that's executed in the past, and you can see the full program state for that point in time, every register, every memory location. Now, obviously, if you're going to do that in a kind of naive way, then that's just a ridiculous amount of data to keep track of. So what we do instead is to kind of exploit the natural determinism of computers. Right? Basically, computers are completely deterministic, except when they're not, right? And so that's why I was mentioning before these classes of non-determinism. I/O being the big one, but scheduling and signals and shared memory and all the others. So we capture just those non-deterministic stimuli, and then in that little demo I showed you, when you step back in time, what's happening under the hood is we're going back to a snapshot and playing that forward to exactly where it needs to be, and then stopping at the right point. So we're not actually we're not capturing everything. We're capturing the minimum that we need to be able to take you back to any point in time. But you have full visibility. All your globals, all your locals, everything rolls back to what it was at that point in time when you step back.
I guess you keep a reachability graph and then keep in track the bare minimum. So
it's just the non-deterministic bits. I mean, it's a classic use case, right? Because they are inherently very non-deterministic. Now, what we would like to have and what we plan to build in the future is the ability to kind of follow that data through the distributed system. And eventually even click next and be able to see go from this node to another. That's left as an exercise to the reader right now. But you have to record each of the nodes in your distributed system and manage the kind of replay of that. So it's a little bit of a manual process. But I mean, compared to not having it, it's still way better. It works beautifully. It just works, right? So because the generated code that's what the program is doing. It's nothing special in that sense. It's just the data it's writing. It then jumps in and executes. So we have lots of customers who have lots of generated code because those are some really nasty issues to debug, right? So this is we get used in that case quite a lot. We don't give you magic in terms of it's still then like using GDB, if you like. You've still got, you're stepping through, you're looking at the hex or whatever it is and all the disassembly of the code that's been generated. But the difference, of course, is with that time travel, it's much more tractable to, figure out, and especially when, and this does happen, the generated code causes memory corruption because you've just got, you haven't got the right prefix or something like that. Correct. Yeah. It's instrumented at runtime. So we don't care whether you're writing hand-tuned assembler or whatever. Yeah.